This conference will now be recorded.
Very good evening, students. Today we are going to learn some important concepts of capacitor combination. So let us start with our discussions for today. So we have so far learned about combination of resistors, okay, in our previous classes, or maybe in this also we have learned about combination of resistors, series combinations, parallel combinations, etc. We have learned for resistors, but we'll see today what happens if we want to calculate equivalent capacitance for a series combination or parallel combination. Just to recap, for a resistors, when there are two resistors of resistance R1 and R2 are in series, then we know the equivalent resistance will be R1 plus R2. And in case of parallel combination, the equivalent equivalent resistance will be 1 by R equivalent is equal to 1 over R1 plus 1 over R2. So this is actually the case in series combination or parallel combination of resistors. But sometime, we may need to use equivalent capacitance. Instead of using so many capacitors, we may also have to use an equivalent capacitor. So in that case, how do we, what will be the formula for equivalent capacitance for series combination and parallel combination? Okay, so this will keep in parallelly, will keep this side. Let me take series combination of capacitors. See, in series combination of capacitors, let me take two capacitors having capacitance C1 and C2, and they are actually connected to a battery of voltage V or potential difference V. Okay, so you need to calculate an equivalent equivalent capacitance of this series combination. So to do the calculation, we need to keep some things in mind. See here, in series case, the amount of charge which is flowing is same for both the capacitors because they are in series. So same charge Q will be flowing throughout the circuit. So C1 will store a amount of charge Q, and same amount of charge Q will be stored by C2 also. But what is the difference? See, difference is that the potential which is dropped across C1, say it is V1 here, and here it is V2. Okay, V2. So this potential difference like potential total sum of the potential drop across C1 and C2 will be equal to V. Sorry, V1 plus V2 is equal to V. So this is actually the key concept here. Otherwise, charge is same for both the capacitors. So in this case, the potential or the voltage applied across this series will be actually divided or distributed. See, V1 is equal to Q by C1, isn't it? And V2 will be is equal to Q by C2. This is the formula from here. And you can see that the potential is inversely proportional to their capacitance. That means the potential will be distributed in the inverse ratio of this capacitance, their capacitance. So V1 by V2, I can write V1 by V2, I can write C2 by C1 like this. Okay. All right, this is fine. So what will take here? This key concept will take from here. And then see, I can write V1 as, you see, I had written already. What is V1? V1 is Q by C1 plus Q by C2 is equal to V. Okay, so this is the thing. Now, if suppose I have to replace, suppose I am replacing this like individual capacitors, and instead of that, I am bringing an equivalent equivalent capacitor, and capacitance of that equivalent capacitor will be such that with the same applied voltage, it can actually store the same amount of charge Q. Okay, same amount of charge will flow through the circuit even if we replace these two individual capacitors C1 and C2 with the uh, equivalent one. So let me take that equivalent capacitance is C equivalent. Okay, and when it is the same voltage applied across the C equivalent, let the Q charge is continuing to flow. Okay, same charge is flowing. So in that case, I can write C is equal to Q by V, or I can write this V is equal to Q by C equivalent. This I can write. Now see, if I give this as equation number 1, this as equation number 2, and obviously this is equation number 3. Now from equation number 2 and 3, what I can write? See, I can write Q by C1 plus Q by C2, that is equal to Q by C equivalent. Okay, or I can write this as 1 by C equivalent is equal to 1 by C1 plus 1 by C2. So this is the equivalent capacitance for a series combination of capacitors. Okay, so this is see, just opposite. In case of series combination of resistors, we get simply sum of the individual resistance. Okay, but in this case it is like sum of the inverse. That means this is actually just similar to the parallel combination of the resistors itself. Okay, sorry, series. Yeah, so parallel combination of resistors are equivalent to series combination of capacitors. Okay, so we have got 1 point. So I'll just now clean maybe this portion and write. So I'll write it here. 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So this is the equation for equivalent capacitance. Okay, for a series combination of resistors. Okay, now we'll see, sorry, parallel combination of capacitors. Okay, in series combination itself, I have to say some points. Let me just tell you a few points here. See, if it is simply two resistors, if two capacitors are there, if two capacitors, if there are two capacitors, then you can actually remember this formula as C equivalent multiplication by divided by addition. This you can keep in mind. Okay, so this will help you for two capacitors. Okay, now second point is that in case of series combination, in series combination, equivalent capacitance is always less than the capacitance of individual capacitor. Individual capacitors. Okay, so we'll move on to another important point in series combination itself. So if there are n capacitors of equal capacitance, if there are n capacitors of equal capacity C are connected in series, then equivalent capacitance will be is C by N. Okay, so these are few points we need to remember. Now we'll see parallel combination. Okay, so see, let me just draw the figure in case of parallel combination. Suppose there are two capacitors of capacitance C1 and C2. They are connected in parallel combination, and battery is connected across this combination, and it can provide potential difference of V. Now in this case, what are the key points? The key points that say if the charge Q is coming out from the battery, it will be actually divided into two branches, Q1, Q2. So Q2 will go here, up, they will come up to here. So here it will be total charge Q1 plus Q2. Okay. So at this position, both will again combine. All right. So the charge is getting divided, and you look here. So this terminal and this terminal are same potential. This terminal and this terminal are at the same potential. So you know the both C1 and C2. So sorry, this is C2. Both C1 and C2 are at the same potential. Both C1 and C2 are they will actually see both C1 and C2 are at same potential. Okay, that means voltage across this is V, voltage across this is also V. All right, so are at same potential. Now how to calculate the equivalent capacitance for this? See, the idea is that the charge, total charge will be this one. So this will be the total charge. So we know Q is equal to C by V. Now charge which is stored, I think this is 1, this is 2. In the capacitor C2 is Q2. Q2 is equal to V by C2. Okay, similarly, Q1 charge will be V by C1. So you can see charge is inversely proportional to C. Capacitor. Okay, C means here capacitor. Okay, so in this case, Q1 plus Q2 is equal to this. Let us write it here itself. So from here we can see. So this I am writing directly the equivalent capacitor also. So C equivalent C1 plus C2. This is V, sorry. C1 plus C2 is equal to E equivalent. Okay, so we can see this is similar to the series combination of resistor. Okay, now we can take small examples. See, we have actually derived these equations for two capacitors, but there could be a number of capacitors in a combination. So in that case, series case, it will be C1 plus C2 plus dot 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 dot. So this is actually equivalent capacitance for a series circuit. Sorry, this is actually the equivalent capacitance for the parallel combination of capacitors. Okay, so this is the thing here. For n number of capacitors, so for n number of capacitors, there will be in case of series 1 over, in series case it will be 1 over C1 plus 1 over C2. Okay, so we have already learned what about like how to calculate the equivalent capacitance of a combination of capacitors in series or in parallel. We have seen already. So now we'll see some of its applications. So I'll just take a simple example for parallel plate capacitor, how to solve the problems. Okay, so let me give you the number 1, 2, 3. Now, what is the equivalent capacitance in this case? These are in series, right? Sorry, parallel combination. So they are relative. So this is actually 6 microfarad. Then change, okay, the charge stored in each capacitor. Charge will be how much? So they are in actually parallel combination, so V is the same. Then Q1 will be 1 microfarad into 6 microfarad. So now you have to find out charge stored in the capacitor. This is 100 actually, 100 volt. Okay, so this is how you have to do it here. Charge will be actually, see, Q is equal to C into V. C1 into V. Q1 means C1 into V. Q2 means C2 into V. C3 into V. Potential is same. Just 100 into this. All this you have to do. Okay, so we have already learned this. We'll just go to the more tricky application of this thing. In case of parallel plate capacitor, when multiple dielectric slabs are used to fill the space between two conducting plates, what happens in that case? So we'll see the situations in those cases. Okay, so look, yesterday we had learned that parallel plate capacitor, when there are two conducting plates, identical conducting plates, and large in size compared to the separation of distance, and if the air medium is there in between, then we have found out that capacitance of the parallel plate capacitor will be C0, that is equal to epsilon 0 A by D. Okay, but the same thing will change if we use a dielectric material. You see, in place of this air, if part of it, okay, partially filled, this we had already discussed yesterday, but there are few more things which we need to discuss here. So partially filled with dielectric medium, okay, dielectric medium. See, this dielectric slab has thickness T, and rest of the thing is D minus T. Yes. So in this case, we had already found out. I'll just briefly say how do we do. Capacitance will be Q by V, right? Q can be written as sigma into A by V, potential difference that we have to calculate. Potential difference can be calculated as V is equal to E into D. So what is E here? E is there, see, for the part, the air, that is sigma by to epsilon 0. Sorry, sigma by epsilon 0. Sigma by epsilon 0 for the part where it is air, yes. Now the part in which the dielectric material is there, then sigma T divided by, see, this will be epsilon, that means epsilon 0 into K. This is the difference. Okay, so we have got potential. So sigma by epsilon 0, this we can take common. Then we have D minus T plus T by K. So this is what we get, the V. Now this is C0, right? This is C0. Okay, whatever it is, let me just put it there in the master equation. C is equal to Q. Q means sigma into A, let us say. So this is sigma into A by V. This is this one. Okay, V is this one. The sigma will go away. So epsilon 0 A by D minus T plus T by K plus T by K. Okay, so that is actually the formula. So when a dielectric material, I'll just clean up everything and I'll write what we have got. This one, epsilon 0 A divided by D minus T plus T by K. So we get this as epsilon 0 A divided by D minus T plus T by K. So this is how we have got for a single slab. Okay. Now at this place itself, there are few points to be understood. Look there. Look here. If suppose there are n number of such slabs, n number of such slabs are given. N number of such slabs are given. So this formula can be replaced by this D minus T1 minus T2. Sorry, this also will be minus T3 then let it be going up to Tn. Okay, this part is there plus T1 by K1 plus T2 by K2. So like that it goes up to the nth term Tn by Kn. Okay, so at this formula, see if D is exactly equal to the sum of this. So if this is the whole thickness or whole space is filled by all these slabs, then see this term will be 0. Okay, because T1, T2, T3, these are actually equal to becoming equal to the thickness of the capacitor. So in that case, you know, this will be C will be this part is anyway 0. So this will be epsilon 0 by A, T1 by K1 plus T2 by K2. So like that, one should do for n times. Okay, so we have seen. Okay, see the same situation I have written here. If suppose there are n dielectric slabs, they are in series. See this I'll just come into like see I had written epsilon 0 A by D minus T1 this thing plus T2 plus dot 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 up to Tn. This plus T1 by K1 plus T2 by K2 and this goes up to n term Tn by Kn and say these are having thickness, say thickness are given. This is K1 electric constant, this is K2, K3, K4 dot 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 it goes up to Kn. Okay, so in this case you know this n see but this n this thickness these slabs are actually filling the whole space between the plate. So this becomes equal. Therefore, this equation will be epsilon 0 A divided by T1 by K1 plus T2 by K2 T3 by K3, and this goes up to Tn by Kn. Okay, so this will be the formula when the whole space is actually occupied or filled by n number of such dielectric slabs. Okay, and here one more good corollary is that if suppose the slab here say, okay, so this is epsilon 0 a by d minus t plus t by k. So in this, suppose this slab is conducting slab, that means this has got direct constant infinite. So if this is conducting, then k will be infinite. If k is infinite, then this formula, so k is infinite, epsilon 0 a by d, this is infinite means this is 0, so d minus t. So this will be the formula. Okay, now if the whole space is occupied by single slab, then say t is equal to d, or d is equal to t, whatever it is. So d is equal to t or t is equal to d. So single slab is inserted. Okay, single slab inserted. So when single thing is there, then we will be having formula sigma epsilon 0 a, sorry, epsilon 0 a divided by c. This term will be 0. This term will be there, d by k. Okay, so that means, you know, epsilon 0 a by a into epsilon 0 a divided by d by k. So this will be the formula when this d is equal to t. The whole space is filled with a single dielectric slab. That is what it is. Now, if the whole space is filled by a conducting slab, then what will happen? Conducting slab. So C will be infinite. Okay, C will be infinite. If the space between if the space between the plates is filled with a single slab, and single conducting slab. Okay, conducting slab, then capacitance will be infinite. So this was So we can see here in this case, see when the space between the two conductors are filled, like is filled with uh, the various dielectric material, then we have already seen normally it is sigma by epsilon 0 A divided by T1 by K1 plus T2 by K2 plus dot dot T, Tk by Kn. Okay, so this is the formula, and you can see it is somewhat like series combination of capacitors. Okay, now we'll take up another situation where the space between the parallel plates will be filled with n number of such slabs of area A1, A2, A3, etc. But the polar, see, it is actually biased in different direction. You can see biasing is this way. That means, equivalent capacitance of parallel arrangement we will get from here. C is equal to C1 plus C2 plus C3, C4. So this is, say, this is actually seeming like, so they say they have the same length anyway. They have small difference uh, of area. See, this is the area of cross section A1. So C1 is equal to K1 epsilon 0 A1 by D in this case plus K2 epsilon 0 A by D2 Kn epsilon 0 An divided by Dn. Okay, so in this case, if suppose A1, A2, A3, they are related to, they are suppose equal to A by N, sorry. Actually, I was trying to convince you here. Okay, so suppose this is An by An. A by n, sorry, A by n for each of them. So this formula becomes K epsilon 0, this term epsilon 0 A into n. So this will be K1 plus K2 plus K3, K4, etc. Okay, so this will be the formula for this kind of parallel arrangement. Okay, so see along the length, the potential is actually varying. Okay, so I think we'll stop it here for today. Next day we'll take up numerical problems on this concept. Okay, this parallel and this series. Okay, this in series. So thank you for your patience. Bye for today.